I'm going to describe a pathway how I believe we could go towards answering that question, how to really find Earth analogs around nearby stars and investigate their properties. And we heard already that the skies are full of planets. And most of these planets are small, and we just heard from Madhu that we're going to learn a ton about all these different kinds of planets that we have accessible today and then in the next few years. But ultimately, and this was already alluded to, we would like to understand not only the diversity of atmospheric compositions, which inform us about formation and evolution of planets, but we would also like to assess habitability, and we would like to address the question of biosignatures. And in the long run, I believe this is something that observations have to provide. We will have to make measurements and then confront the data with those measurements. Without measurements, we're not going to really learn a lot, I believe. So you've heard that we know already so many planets, and then the question is, so how come that we're not really able yet to address these questions, at least for the terrestrial planets, the ones that are very similar to Earth or Mars or Venus? And the reason is it's not for lack of trying, right? It's simply a question of how to detect those planets and how to investigate those planets. And again, it's not to blame the current generation of observers that they did it wrong, but it's just what was available. And I would like to argue that we have to go one step beyond in the coming 10 years or so to answer this question. So let's remind ourselves how we did all these detections. So just very briefly, because this hasn't been really shown yet. So on the left-hand side, you see a very successful technique how to find planets, and the experts is here in the front row. Didier can tell you all about it. So basically, you infer the existence of a planet by looking at the star, and the star wobbles as the planet pulls on the star and moves the center of gravity of the star. So this is an indirect technique that gives you access to the mass of the planet and to some orbital elements, but you do not see the planet directly. And this is obviously a limitation if you would like to understand the atmospheric composition and look for habitable conditions and biosignature. On the right-hand side, you see another technique that is very successful. This is the technique that Madhu was referring to, which is the transit technique, that in principle you could hope that if you're lucky enough, the orbital plane of an exoplanet will be oriented such that it passes in front of the star, leading to a periodic dimming. And from this, you can also infer the existence of the planet, and you can measure its radius, but it's also an indirect technique. There are ways, and this is what Madhu alluded to, right? You can get information about the atmosphere in some cases, but most of the planets out there, they do not transit, right? The orbits are randomly oriented in the plane of the sky. So to first order for every planet you find transiting, you're not seeing 99 other planets. So this tells you automatically that you have to go to much, much larger distances for detecting these planets. Or in other words, you're not seeing many of the planets that are in our immediate solar neighborhood, and this is, of course, a pity. So let's change technique. Let's try this direct detection approach that was already mentioned. And this is also, for me, a very, very important picture, because this is Earth, as already explained. Right? This is a picture of Earth taken from the Voyager spacecraft. And now imagine you can take a picture of a planet. Then you're able to look at the spectrum of the planet directly. So it's a direct detection. And if you do this for Earth, and also this has been shown already in different ways today, if you can look at the light as it spreads over different wavelengths and look at the intensity as a function of wavelength, you're going to see a spectrum like this in case of the Earth. This is an average spectrum of our home planet. And you can see all these different absorption features. And this is what allows you to learn something about the atmospheric composition, about the surface condition, and ultimately also about looking for biosignatures. And two of them were already mentioned today. So we have ozone, which is a direct photochemical byproduct of the oxygen that is produced by the plants on our planet. And you have methane here. And these two, we could, in principle, infer on other exoplanets as well from remote sensing, from taking a picture of a planet. It doesn't even have to be a special resolved picture, but measuring the flux of the planet directly and then looking at the different absorption features. And this is actually a very important plot in the context of the center, because what I'm showing here is our home planet. We know what to look for, but there might be other biosignatures. And again, Madhu mentioned this already. If it's very important to understand what imprints life can leave in atmospheres, for us to know what we're looking for and help us to interpret the data we're gonna look for. And ultimately, it helps us to design instruments. We always use Earth as a reference case, which I think is fair. But there might be so many other ways how life could leave imprints. in an atmosphere. And for this, we need to work together with a chemist, with a biologist, and with earth science to understand the false positives, how a planet can fool us, but also to learn what else to look for. So this is the landscape, how I see it, that for the direct detection, don't get me wrong, because I put a big red cross here next to James Webb and it was going to kill me, right? So this is for the direct detection of exoplanets, right? It's so taking pictures of exoplanets. So on the left-hand side, you see where we are today, Earth, 8 to 10 meter telescopes on the ground, and James Webb. We're not going to detect many of these small terrestrial planets directly. Then we have the ELTs coming up, 30 to 40 meter telescopes, and eventually the next flagship missions. So with the middle one, for the large ground-based telescopes, we're going to get a few terrestrial planets, I think, but we need large, really large space missions to detect dozens of Earth-sized exoplanets and do statistics on those. And now if you think again about the center here, so in the next 10 years, we will have first images from the ELT. And in order to build large missions, you have to start early. They take long. So we don't have to wait. If we want this to happen, we have to start building. So let's go to the ELT, and then let's go to one of these big space missions. This is the ESO ELT, the world's largest telescope ever built. It has 39 meter primary mirror. So the current largest one have roughly 10 meter, right? So this is a factor of 4 increase in collecting area, and it's gonna be unrivaled and unparalleled for decades to come. And sorry, but I have to say this is even bigger than the American telescopes. So there's going to be 2 competing telescopes in the US, but the European one, for once, is the largest. This is obviously an artist's impression, right? But it's happening. And this is very, very important to realize. This is a recent picture from the mountain in Chile where this thing is going to be built. So there is progress. They chopped up the mountaintop and they start building the telescope. Yeah, they did. No kidding. They chopped up the mountaintop and they start building the structure for the main dome. So it is happening. And there's one instrument that we're involved in, and I'm actually the project scientist for this instrument, which is called METIS. And we hope that it gets first light towards the end of this decade. And why am I so excited about this project? Because this instrument may be the one to take the first picture of a terrestrial exoplanet around a nearby star. I kind of prove this to you because we don't know whether some of the nearest stars do have actually rocky planets around them, because they're very hard to measure with the techniques I already described to you. But if they had, there's a chance that we're going to take a picture of those. So this is a simulation we did for this instrument. This is a picture where we point the biggest telescope that is ever going to be built to one of the nearest stars, Alpha Centauri. Sort of counterintuitive if you think about it, right? You take the largest telescope and you point it to one of the brightest objects in the sky. But if you do that, you are actually able, with 1 or 2 nights of observing time, to find if they exist these dots. So these dots, what do they represent? They represent Earth-sized planets around the star. And one is exactly in the center of the habitable zone, the slightly fainter one to the right, and the other one is halfway closer to the star. So this is 1 night of integration time, and we could do this for a handful of nearby stars. And the hope is that this will trigger even more excitement in this field, that we can take pictures of rocky planets around nearby stars. And then we have to go even bigger, and then we have to go to space. And this is again an artist's impression for what we call the LIFE mission, and this is the LIFE initiative. LIFE stands for Large Interferometer for Exoplanets. I think it's a very useful acronym, if you ask me. And the idea here is to combine basically the ELT, the size of the ELT, with the sensitivity from the James Webb Space Telescope. The James Webb Space Telescope is in space, so it's very sensitive. And on the ground, you're not so sensitive because you're looking to the disturbing effects of the Earth atmosphere. So you want to combine the 2 aspects. You want to build a large telescope in space. Turns out to be tricky to launch a single mirror, 30-meter telescope into space. So you have to work around this. And the idea is to use several smaller ones. On the left-hand side, you see 4 telescopes, roughly the size of a Hubble telescope, 2 to 3 meters, that work together as a single large telescope, and they send the light to this beam combiner here. And by doing that, you are able to achieve these 2 requirements: the sensitivity of a large space-based telescope, and they have sufficient spatial resolution. Without going too much into the detail here, I would simply like to show two things. One is a classical number that is important for these future large missions, which is how many planets are you going to get? And I show this in comparison to some of the flagships that NASA is currently studying. So on the left-hand side, you see results from very detailed studies that NASA did over the last 2 or 3 years, where you ask the question, how many planets can you expect from a future large mission? And they use a different technique. It's not the same technique, it's kind of a different observational technique. And on the right-hand side, you see the results from our European-led LIFE initiative, where we want to make sure that we are comparable to those numbers. And what is very important is not only the absolute number, we're talking about literally hundreds of planets, but very importantly, look at the green bar down here. These are smallish, rocky, and super-Earth planets. These are the ones that are very precious to understand the diversity and look for habitability and look for biosignatures. And these are the ones where we have troubles analyzing them with James Webb today. And then eventually, if you are able to do that, if you find those many planets, you can look and investigate the differences. You see here Mars, Venus, and Earth spectra, how they differ. This is the wavelength range that we consider for our LIFE initiative. And the reason is because this is where the temperate planets emit most of their spectra. Most of the light coming from these wavelengths. And you can then start looking for these biosignatures and compare which planets do show them and which don't. The good thing is that this concept has been recognized as a candidate for a future mission, an L-class mission within the ESA program. Last year, a report came out where it was recognized that a mission that looks at the atmospheres of temperate exoplanets should be a top priority for ESA. It could solidify European leadership in exoplanet science, and looking for potential biosignatures would be an outstanding breakthrough. This does not mean it's a selected mission already, but it means we have a way into the science program of ESA, and now we simply have to make it happen. Thank you very much.